Hello and welcome to my fourth lab about bar magnets. So first, the key concepts, really you only need to understand the Biot-Savart law, which is the expression of the magnetic field equation. And specifically, this is for a coil wire. And you can see that by the current and the length of the coil. But this is also applicable for bar magnets. We're using that. And it has a distance dependence. And we're going to be calculating that. And it's essentially all of the constants involved, including you can think about it as the charge of the magnetic moment, as well as the distance, and then to some power. And we're going to linearize with this equation right here. So what are the goals, purposes, and outcomes? The goals are to measure the X, Y, and Z components of the magnetic field with this magnetometer at PHYS at different locations on and off the axis. We're going to linearize that. We're going to find the moment of the bar magnet. We're going to simulate it. We're going to compare. So basically, this is going to be utilizing that Biot-Savart law. We're going to find that distance, power, n. We're going to see how the simulations compare, and we're going to demonstrate the validity of the law as an expression of a quantifiable magnetic moment. In the experiment, we found out that the magnetic field magnitude decreases with increased distance. Qualitatively, that the moment is 2.992 amp meters squared, and that the measured field is, according to this equation from the linearization, and at a 45-degree angle, a distance of about 0.18 meters, that it had a magnetic field of 1.52. In the simulation, using this same magnetic dipole moment, we actually got a number that is half the size. That's strange. So the introduction, the setup, essentially you have a system which is just a magnetic meteor chip, right, which you can see right here, and then the effect of Earth's magnetic field, which you can think of as straight up and down relative to your location, and then as well as that, some small magnet at this 45-degree angle, which is going to have approximately this magnetic field impact. Then you're going to have this magenta outcome. So these surroundings are the magnet, the Earth, and then anything else in the room. Specifically, the table is the most immediate thing, and then there's also going to be some things in the system that we're not going to take into account, such as phones, and that's just going to introduce some error. So what is this diagram here? This is essentially showing two things. Number one, this is how we're getting that 45-degree angle observation point, and that's going to be useful as a comparison for the simulation and for the experiment. And we're going to get this red X on the phone, which is where we're going to think the magnetometer chip is, by a process that essentially boils down to making the X and Y axis of the magnetometer equal to 0 by changing the orientation of the phone in alignment with this magnetic moment. So here's the spreadsheet. You can see different distances lining up with the different magnetic field strengths, which you linearize with this equation here, which I've exploded. And essentially, this equation here represents this equation, where you can see the magnitude of the magnetic field, that power, the distance, and those constants, which gives us these values. Using those values, we can make a simulation. And this simulation is going to be according to the Biot-Savart law, which we can rewrite without the cross product like so. You can see here the constants. This is going to be representing the magnetic moment itself, and this is going to be representing how it changes dependent on distance, without regard to orientation. You can see that transplanted here, as well as that input the moment, and then just for some demonstration in the simulation, visually, you have these different vectors representing the axes, and then I didn't include the duplications, but these are all of the axes here. And then finally, you're going to find the dipole, the impact of the dipole moment of the magnetic field at that 45-degree location, which you can see down here. So at that 45 observation, which you can see here in magenta, and actually at this distance, which matches experimentation perfectly, you can see that it gives this magnetic field strength, which we already went over, is about half. So the conclusions, the distance and magnitude of the magnetic field are inversely related. You can see that it lines up like this. As the magnetic field increases, the distance decreases. Vice versa. Here's the moment. You can see the difference in the experiment and simulation about double. Why does it contradict this? In my opinion, I think there's some issue with one of the equations somewhere. It could be in the Excel sheet. It could be in the assumed equation here. It could be anywhere, but the fact that it's about double and it lines up pretty well, to me, demonstrates that there is something wrong. It could also be any of these sources of distortion: human error, phone magnetometer error, so just the apps being kind of bad and the phone being kind of bad, but also the external Earth's field not being properly accounted for. Is that possible? Absolutely. The discussion question 1, if we were to put the meter stick at some other angle, how would it respond? So the Earth's magnetic field is always going to be pointing in a certain direction, independent of this meter stick. And essentially, it would contribute the same magnitude. It would just change on the X and Y axis depending on how you move that axis. And it's just going to be according to normal trigonometry. But Z would not change. If you stuck two identical magnets together and run the experiment, it depends on the orientation. If the moments are in the same direction, then superposition dictates that the combined magnetic field will be approximately double. And if they're in opposite direction, then superposition says that they will be approximately zero. The distance measurements to achieve certain field strengths will then change according to the same relationship, except that they will be double in magnitude or about zero. Thank you.